Okay, so obviously this function lambda to the power k divided by k factorial e to the power minus lambda. Obviously this is a non-negative function because there is nothing negative here. Lambda is positive, k is a positive integer, and the exponential function is always a non-negative. So the function is always positive. So it can be a probability. And well, I'm not going to do it here, but it's always bounded by 1 also. We'll just look at the sum. So let's see if the sum of the PMF entries adds up to 1. Um, so this is the sum of k from 0 to infinity of lambda to power k over k factorial times e to power minus lambda. This term here is independent of k, so I take it out of the summation. And what remains is, well, I don't know if you recognize this directly, but this is the Taylor series expansion of e to the power lambda. Let me just give you this. E to the power x can be written as the sum from k0 to infinity, um, x to power k divided by k factorial. This is directly the Taylor series expansion of the exponential function. So what we see here is directly e to the power lambda, because, well, it's the summation limit goes to infinity. So this is directly equal to e to the power lambda multiplied by e to the power minus lambda. You get 1 as expected. So the sum of these terms add up to 1, which means this is a legitimate distribution. Okay, next, let's look at the statistics of this distribution. Well, from the definition, we know the mean number of events is assumed to be known and equal to lambda. So we expect the expected value to be lambda, but let's see if that turns out to be the case. So expected value is computed by this sum, k times the PMF. The PMF is here. And here, again, you see, due to this k factor here, starting from 0 is unnecessary because k equals 0 will give me no contribution. That term will be 0. So I can start the sum from 1. And also, I can take out this e to the power minus lambda term outside of the sum. And I'll also take one of the lambdas from lambda to the power k, and this will become lambda to the power k minus 1. And this k will cancel out the k in k factorial, so I will have k minus 1 factorial here. And at this point, I'm going to make again k minus 1 equals I transformation. So this will, the sum will be from, instead of k equals 1 to infinity, it will be from I equals 0 to infinity. And here I have lambda to the power I divided by I factorial. Again, this sum here is a Taylor series expansion of e to the power lambda. So I have e to the power lambda, canceling out this e to the power minus lambda. Therefore, I just have this lambda here. As expected, the mean value is lambda. So no problem here. What about the second moment and the variance? For the second moment, again, you have the PMF here and we have the k squared term. We will compute this sum. Now, as earlier, I'll write k squared as k squared minus k plus k. So this will be k times k minus 1. Okay. And obviously, since you have k squared here, um, well, yeah, in this term, I have k times k minus 1. I separated this term and this term appears here. Okay. And in this term, I can start the sum from 2 instead of 0 because the first two terms, k equals 0 due to this one and k equals 1 due to this one, will give me 0. Okay, so I start this from k equals 2. What I'm doing is I have k times k minus 1 here. I eliminate those terms from k factorial, so I will have k minus 2 factorial here. And I take out two lambdas out. I have lambda squared. And here I have lambda to the power k minus 2. And this e to the power minus lambda term that appears here outside of the sum because it's independent of k. And you see this here again can be expressed as when you define k minus 2 as I, the sum from I equals 0 to infinity, lambda to the power I over I factorial. So this here again will be e to the power lambda. And that multiplied by e to the power minus lambda times lambda square. What about this term? Now at this point again, this should be recognizable to you by the expected value of the Poisson distribution, because this is the PMF and I have a K here. Okay, so it may not be obvious to you at first, but after some time, these things should come to you. Okay, so this is the PMF of the Poisson distribution. You should recognize it. And when you multiply it by K and add them up, you should recognize this sum as the expected value of the Poisson distribution. So just put lambda in this case. Okay, so that is lambda. So I have here e to the minus lambda canceled out with e to the lambda. I just have lambda square plus lambda. So this is the second moment. Okay, so to obtain the variance, what remains is subtract from the second moment just square of the mean, and the result is just lambda. So the variance and the expected value of the Poisson distribution is equal in value and equal to lambda.